We're going to talk about angles and scalar product in R2 and the relation between them. In this lecture, V is going to denote Rn. For the moment, V will be just R squared. As a mathematical object, an angle is a real number. It is usually associated to particular regions of R squared, which we will call angular regions. So to an angular region, there is associated the real number called angle of the angular region. Definition: an angular region is a subset of R squared whose boundary is the union of two rays originating from the same point. Let's make an example and draw a pair of such rays. The complement R squared minus the union of the two rays is the disjoint union of two angular regions. One is called T1 and it is the upper part, and another one we will call T2, which is the lower part. These are infinite rays, so the complement is disconnected, and one connected component is the T1 here on the top, and another one is T2 here on the bottom. Definition: let T be an angular region with corner C. Then the angle of T is the length of the arc U. The arc U is constructed taking a radius 1 circumference centered in C. So this is C. We take a radius 1 circumference centered in C, and we take the length of the arc that is included in the angular region. We have our angular regions. They are bounded by these two rays. They are starting from the same point in R squared. This is called the corner. And we take, suppose that this is length 1 segment, so we take the circumference of radius 1 centered in the corner of the angular regions, and we draw a circumference. Now we have two regions. One is T and the other is the one here on the bottom. Suppose that we are referring to the region T. Then the angle of the angular region T is precisely the length of this arc. So the arc U is the intersection of the circumference with the region T. So it is precisely what we denoted here with the blue color. If we wanted to consider the other angular region, the one on the bottom, then the arc U would be drawn as follows. So we take again the same picture as before, and then the region we are referring now is the lower one, the lower angular region. So we have to take the intersection of this radius 1 circle centered in the corner with T. So once again we get this. So U is the length of this arc this time. Sometimes this is called the angle measured in radians. 1 radian corresponding to the number 1. If we take the length of these arcs, whether it be this one or this one, assuming that the unit of measure is the 1, referring to 1 as the radius of the circumference, we will of course know that the length of the entire circumference is 2 pi, and 2 pi is 6.28 and counting. And the 6 is referring to a unit of measure, which is the radius in this case. So each unit of measure is called a radians on this definition, a radian. An alternative measure of angles is called the degrees, and it is obtained from the measuring radians by multiplying the measuring radians by 180 divided by pi. Therefore, since the whole circumference is 2 pi, if we multiply 180 divided by pi, we get 360, which is the usual angular measure for the whole circumference. Let us now come to this very important discussion about the angle between vectors in R². So I stress the word vectors because before we defined the angle for angular regions. So now we switch to vectors. And the definition of angle between vectors will have to pass through the notion of angular region that we have just given. So how do we associate to vectors an angular region? Let W and Z be two vectors in R². As always stressed in this course, vectors in Rn are the same thing as points. Hence, they should be drawn in the same way. So we have 2 points here, one dot referring to W and one dot referring to Z. The angular region associated to this pair of vectors is determined by the rays RW and RZ that we obtain by connecting the two vectors to the origin. So the corner of the angular regions associated to vectors is always the origin of R². However, as we have seen in the previous example, there are two such regions. In this picture, there is one region that is here on the top and another region which is on the bottom, angular regions, that is. By convention, we define the angle between W and Z to be the only one between 0 and pi as angle. Which one of these angular regions we are going to choose then? Of course, if we see that one is the bottom one, the length of the circumference is going to be, of course, greater than pi, and the top one is going to be less than pi. So in this case, the angle between W and Z is going to be the angle of the angular region of the region T up here and not the one on the bottom, by this convention. So these univocally determine the angle between W and Z. In the case W and Z are one opposite to the other, therefore the two regions have angle exactly equal to pi in both cases. Then it doesn't really matter which region we take associated to the angles, because in both cases the angle will be just pi. Therefore, even in that case, which is the extreme one, it is one corresponding to pi, it is well defined. The angle is well defined. Notice that if the angular regions have different angles, there is only one in the 0 pi range. Therefore, in our picture, the angular region is the one labeled T. For a geometrical interpretation of inner products, it is important to remark that an inner product is completely determined by its action on vectors of norm 1. See lecture 10.1 for the definition of norm of a vector. So here, now, in the rest of the lecture, we will try to relate inner products with the angle between vectors. Indeed, for any vector v in the vector space big V, V divided norm of V has always norm 1. Therefore, the inner product of W with Z can be rewritten as norm of W times the vector W divided by norm of W. And of course, this vector is W itself. We can just cancel out the norm of W here and here. And we do the same with the vector Z. but by bilinearity of the inner product, in this case with respect of multiplication of scalars, we can factor out both norms from this operation and have this equality. Norm of W times norm of Z times the inner product of W divided by its norm with the Z divided by its norm. And both these vectors have norm 1 as claimed before. So the inner product of generic vectors W and Z is reduced to knowing the inner product of vectors of length 1, of norm 1. Okay. With this in mind, we now restrict our attention to a very special kind of inner product in Rn. I anticipated its name in the previous lecture, but let me define it in a more explicit way right now. So the inner product we will be considering is the one corresponding to the matrix, the identity matrix. See lecture 10.1. We have seen in this lecture that in Rn we can express inner products by means of a symmetric matrix. Vice versa, if we have a symmetric matrix, we have a uniquely defined inner product associated to it. In this case, we are considering the inner product corresponding to the identity matrix in Rn. Or equivalently, this inner product can be defined to be the one acting on two column vectors, x1 through xn and y1 through yn, by the following formula: sums of xi times yi for I that goes from 1 to n. This is the inner product associated to the identity matrix. This product is called Euclidean, and for n equals to 2 is called the scalar product or dot product. And it has very interesting geometrical properties that relate to the angle, as we defined before, between vectors. Let W and Z in R squared such that norm of W and norm of Z equals to 1. We have seen that we can restrict our attention to these norm 1 vectors in R squared in order to understand what will be the inner product between W and Z for general inner products. Well, in this particular case, we are choosing a very special one. And let's interpret the inner product between W and Z in such case in terms of angles between W and Z, as we defined before. Then, since both vectors have norm 1, we can express them as W equals the cosine of a certain angle alpha and sine of alpha, and Z will be cosine of beta and sine of beta for some angles alpha and beta. Let's draw the relevant picture. We have a unit circle here. All the vectors we are restricting our attention to lie on this unit circle. We pick two random vectors on it, W and Z, and their coordinates are, by definition of cosine and sine, precisely the cosine of alpha for W, where alpha is this green angle. Okay, so the abscissa of W is going to be cosine of alpha, and the ordinate is going to be sine of alpha, and the same for Z. So angle beta is marked in yellow in this case, and the cosine of beta is going to be the abscissa of Z, and the sine of beta the ordinate of Z. Sine beta, cosine alpha, sine alpha. By definition, the scalar product at this point of W and Z is by definition of scalar product, is going to be what? The first coordinate of w times the first coordinate of z, so cosine of alpha times cosine of beta, plus the second coordinate of w times the second coordinate of z. So we get this expression. But by the well-known trigonometric formula, this is precisely equal to the cosine of alpha minus beta. So this new angle, alpha minus beta, which corresponds to this length from z to w. Okay. In other words, the scalar product of w and z is the cosine of the angle between the two vectors. Okay. So if we take the cosine of this angle, we get precisely the scalar product of w and z. This shows that for any a and b in R squared, the dot product, the scalar product of a and b equals, well, if they were of norm 1, they would be equal to cosine of theta, where theta is the angle between a and b. But now we are just considering them to be any two vectors in R squared. And as we have seen before, the expression of the scalar product between two vectors in function of length 1 or norm 1 vectors was obtained by pulling out of the operation of scalar product the norms of A and B, the norms of the vectors. So plugging in the value for the scalar product of the norm 1 vectors, which is we have just shown to be cosine of theta, we prove this equality. So it is cosine of theta, and this is the scalar product of the A modulo norm of A and B modulo norm of B, multiplied by norm of A times norm of B. We have two very important remarks to finish up the lecture. The first one we call fundamental. From this equation, we see that the scalar product between v and w is 0 if and only if cosine of theta is 0. We are assuming both of these vectors to be non-zero. If one of the two vectors is 0, the 0 vector, of course, the scalar product will be 0. If both vectors are non-zero, then their scalar product will be 0 if and only if this term will be 0. Cosine of theta is 0. But cosine of theta is 0 if and only if theta is pi over 2. Hence, v and w are orthogonal if and only if the scalar product between v and w is 0. Here I'm referring to orthogonal in the classical sense, meaning that their angle is pi over 2 between them, so like 90 degrees angle between them. Okay, so this gives a very useful criteria to show that two vectors are orthogonal. We just have to take their scalar product with the very easy formula that the scalar product assumes and check that the two vectors, their scalar product is 0. The second important remark is the following. The notion of angle between v and w of Rn has a geometrical interpretation entirely similar to that of R squared. So far we have used the fact that the vectors we were taking the inner product of were vectors of R squared, and now we want to extend the same consideration, the same relation between angle and the scalar product to arbitrary vectors in Rn and not just R squared. Since we can simply consider a plane H in Rn containing v and w. Now this plane containing two vectors of Rn is unique if and only if v and w are linearly independent. If they are not linearly independent, just take any plane containing both v and w. Then we can give to H, let H be this plane, we can give H the an inner product, which we will denote by inner product with the H here, defined as inner product between A and B through this notion regarding H, is defined to be the same inner product that we have in Rn. So in this case, if we are considering the scalar product, the one associated to the identity matrix, this will give an inner product to H for any A and B in H. Then the above formula that we wrote in yellow, relating the inner product, the scalar product, inner square, to the angle theta between the vectors A and B, simply extends in exactly the same way to this inner product of H.